Hello and welcome back. Today we'll get into a look at Section 9.4 on vectors. So first off, what we're talking about when we refer to a vector, we have a directed line segment. That's all it takes to be a vector. So line segment, remember we have basically two endpoints, so it's not a ray or a line. Directed, all we mean is that we have a starting point and an ending point. So this is sort of a common notation for PQ. I have seen it sometimes with an arrow instead of the sort of half arrow. That can kind of vary book to book. Typically, though, vectors will be referred to with one letter. In the notation in the books, they'll be in bold. And they pick names like V or W. Since we can't really write in bold in just pencils and pens, sometimes you'll see those arrows above them to indicate that it's not a variable, that it is in fact a vector that we're referring to. Usually it's clear from context that we're referring to vectors. But again, just some notation that you may see elsewhere. So we'll start with the idea of performing operations on these vectors, and we'll start with just the most basic of our operations, addition. I'm just putting the grid on here to kind of make things a little easier to read. So let's say that vector V takes us, well, let's go up to and write 1, 2, 3. So we'll name that vector V. And vector W, let's say we'll go up 4 and write 1. So this is a geometric interpretation of vector V plus vector W. I would just connect the starting point for V with the end point for W, and that would be my sum. This is vector V plus W. Now you should be able to convince yourself that this is commutative. If I start here and draw my W first, which want, remember, up 4 and write 1. So up 1, 2, 3, 4 and write 1. And then V had me go up 2 and write 3. So up 1, 2 and write 1, 2, and 3. We land on the very same point, whether we took care of V first or W first. So vector addition is commutative. It's also associative. There also exists the zero vector, which would basically be a point, just sort of holding still. We don't go from a starting point to an endpoint. Our starting and end point are the same on the 0 vector. And that 0 vector would return us to the starting point. So v plus 0 would return us to v. Similarly, 0 plus v would return a v as well. We also would have not equals v minus v would get us to the 0 vector. Basically, if v took us up 2 and right 3, minus v would take us back down that same path, and we would land right back where we started. V minus w, basically instead of going, if w said go to the right 1 and up 4, minus w would just say, okay, go to the left 1 and drop down 4. So just like in sign numbers, subtracting vectors is the same as adding their opposite. So one thing that is a little bit new though to vectors, the idea of the scalar multiple. So we're going to let alpha, temporarily we'll let it be greater than 0. Then the vector alpha v so some positive constant times vector v. It's still a vector in the direction of v with magnitude so magnitude being the size of the vector, the distance. Alpha times magnitude of the original. So these double lines indicate magnitude of v. So how far apart were the start and end points on v? Multiply that by alpha. Similarly, if alpha is less than 0, then it's a vector in the opposite direction of v. But the magnitude would be absolute of alpha times magnitude of v. Now some properties of magnitude. Magnitude is the distance between points, so it has to be at least 0. Magnitude of the opposite of a vector is the same as its original vector. We're just moving in the opposite direction. We don't move a different distance. And the magnitude of alpha v is the same as what we talked about before, absolute of alpha times magnitude of v. One useful tool in vectors is the unit vector. And we weren't super clever with naming that. It's named that because it is a distance of 1 of whatever unit we're measuring. Now there's 2 common notations for vectors once we start putting numbers to them. Sometimes we have these little, they look like inequality symbols, but they're not. So we use these guys instead of parentheses. just to differentiate that this is not an ordered pair, this is a directed distance. Another way they denote the same thing is A times I plus B times J. So the I direction is basically left and right, J direction is up and down. So for example, if V equals, let's say 1, 6, and W is 7I minus 9 times J, we can do operations on those. We can do V plus W. So that would be 1 plus 7 together with 6 plus a negative 9. So the vector that's the sum of those two would have us go to the right 8 units and drop down 3 units, which again we could write it either this way, or you could also see it as 8I minus 3J. Those would mean the same thing, just two different ways of expressing that. V minus W works exactly how you think. Again, just respective pieces. So 1 minus 7, 6 minus negative 9. So V minus W would have us take a starting point, move 6 units left, and then 15 units up. And again, you may also see it written as negative 6I plus 15 times J. You should be able to pretty easily convince yourself that, much like in real number adding and subtracting, subtracting with vectors, the order does matter. Subtraction is not a commutative operation. In fact, I would recommend pausing the video, see if you can find this vector real quick. Okay, welcome back. So now we start at 7 and subtract the 1, start at negative 9, subtract the 6. So we would have a 6 and a negative 15, or 6I minus 15J. Let's see, what else can we do? Scalar multiples, we'll do 5V. On that, each piece, we just multiply by the 5. So 5 by 1, comma, 5 by 6. So 5V would be a vector, same direction, but that goes 5 to the right and 30 up from the starting point. Another useful tool, again, the unit vector. We'll keep the same V from the previous page. We'll keep that at a 1, 6. Basically, I want to keep the same idea, the same ratio of right or left to up, down, only I want the distance to be a 1. Well, first I would find what the magnitude of V is, and for that you can just kind of draw your little right triangle, well, just like from your college algebra days. So we started at this point P, we went to the right one, we went up 6, landed on Q. So this is our vector. The size of that vector, the magnitude, we just use the Pythagorean theorem. So vectors magnitude squared would be 1 squared plus 6 squared, so magnitude of the vector would just be the square root of 1 squared plus 6 squared. So this vector has a length of root 37. So if I want to keep going in that same direction as v, but have a length of 1, we'll just divide vector v by the magnitude of v. So our unit vector for this guy, we'll take the 1, 6 and divide by root 37. So that's 1 over root 37, 6 over root 37, and we can just rationalize those guys. So then our unit vector would be root 37 over 37 with 6 root 37 over 37. And you should be able to convince yourself that if you drew out a vector with these measurements, that your hypotenuse should land you on a 1. So next step, ask us to just kind of explore what we know. So we're going to find a vector such that we have a magnitude of 20 and the angle from the positive x-axis is 135 degrees. Well, first we'll find u for this. So for that, we can just make a quick sketch on our unit circle. So a radius of 135 degrees, so that's a 90 plus a 45. So that means our x-coordinate, we went from 0 on the x to negative root 2 over 2. So our distance in the x direction would be negative root 2 over 2. Our distance on the y, we went from 0 to positive root 2 over 2, so positive root 2 over 2. So that's our unit vector. Now we want it to have a magnitude of 20. So then v would be equal to 20 times u. So then v is negative 10 root 2, 10 root 2. So same direction as our unit vector, but then we want a length of 20. And that should make sense. That's really just kind of juggling this formula, getting the v by itself. Unit vector times the magnitude we're looking for on v. So it's more taking advantage of the idea of the scalar multiple. So next we'll look at the angle of v given its coordinates. So v, let's say they tell us it's 16, 16 root 3. Again, they also could have told us v is 16i plus 16 root 3j, and it would mean the same thing. So they could make it look two different ways. They're exactly equivalent to one another. So thinking about these as being sort of related to the x and y in terms of direction and distance from the 0, this is basically related to then cosine. This is related to sine. So the one thing that takes into account both of those would be tangent. So then the tangent of alpha would be 16 root 3 over 16, which is root 3, which we can turn into root 3 over 2 over 1/2. So our, on the unit circle, y value of root 3 over 2 and x value of 1/2. And these are ordered pairs at this point. That angle then is 60 degrees, so alpha is 60 degrees if they're reporting it in degrees, or if they're reporting it in radians, alpha is then pi over 3. All right, so from 9.4, the section on vectors, I would try 11 to 71 on the odds, and again, I'll try to make an equivalent one for the My Math Lab fans. If you have any questions, please get in touch. Otherwise, I will see you next time. Stay safe out there.